Yeah, if somebody wants to cover GMAT, it's a good sheet to try. Okay, cool. Let's get started with probability. The thing with probability is, as I'm sure you guys know and understand, if somebody does probability, does PNC well, understands and is able to solve PNC questions well, then I would say that takes away 30% of the problem that people face in probability, not more, because probability obviously has its own challenges, and we're going to see some of those challenges. Definition, we'll start with the definition and concept. So, essentially there's just two main category of concepts. One that I'll reduce right now, and then there's another type, and then I'll just probably just ask you to solve questions. That's all really there is to probability. PNC is a little more content than probability. Probability doesn't have as much. And I'm not going to give you formulae as such. There are not many, but there are a few different formulae available for probability, and you don't really need them if you understand the concept well. So I am going to focus on the basics today, basic concepts, and that starts obviously with the definition. Probability is definitely favorable outcomes by total outcomes. Yeah. Since favorable outcomes can never be more than total outcomes. Yeah. Therefore, probability is always probability of any event happening. Let me call that event A. Yeah. You could have called it E, whatever you want to call it. Probability of an event A happening will always be less than or equal to 1. And it is, of course, the average likelihood. Very important. Average likelihood of any event happening. When we say that we roll a dice and the probability of getting a 2 on the top surface is 1 by 6. That is the average likelihood. It is likely that if you roll the dice 6 times, you won't get a 2. It's likely that if you roll the dice 60 times, you still won't get a 2. But yeah, probability is the average likelihood, and it's mathematical in that sense. Very important next formula and next concept: probability of favorable plus probability of non-favorable events is 1. So there's nothing in between. Either the event is happening. So it's either the event will happen or it will not happen. There's nothing in between when it comes to either PNC or probability. You may remember we had discussed this when we discussed PNC. In PNC, we talked about favorable number of ways. As an approach, this was very important that favorable number of ways can be calculated as total minus unfavorable. Yeah, so this is very similar. Concept number 2, part number 2 is very similar to that, in which probability of an event happening, favorable probability, let's say PA, A is that event, is nothing but 1 minus the probability of A not happening. Probability of A not happening is only denoted by A dash. Just relevant, in case you see this somewhere in some reference book. So please remember this. Probability of an event happening is nothing but 1, which is the total probability, minus probability of that event not happening. Just like we had here. Favorable ways is total ways minus unfavorable ways. Here, and in all cases, total probability always happens to be 1. Yeah, I hope this is clear and simple. Hopefully, this should not be a challenge. And the next one is important. And before you jump to the formula, no, not necessarily. We'll come to the formula later. Let me know what you think of mutually exclusive events. What do you understand from the term mutually exclusive event?
So suppose if I am present here, I can't be present at another place at the same time.
Okay. So you're being present in front of the session wherever you are right now, yeah, and being present in some other place doing something else they're mutually exclusive events. Okay. Any other example?
Maybe a coin toss. So you will either get true or false. You cannot get both.
Coin toss is heads or tails.
Sorry.
I mean, yeah. In a coin toss, so if I toss the coins exactly once, then getting a head or getting a tail, these are two mutually exclusive events. Can't happen at the same time. Yeah. If I roll a dice, getting a 2 or getting a 4 on the top face of the same dice are mutually exclusive events. They can't happen at the same time. Yeah. So also let's talk about independent events. If we understand what mutually exclusive events are, and we'll see what that means mathematically. Let's first discuss what independent events are. What are independent events, guys? What are independent events in your opinion?
Two coin tosses. They're independent of each other.
Okay. And two coin tosses are very generic. How do you associate? Okay, let's say, how do you associate probability with coin tosses? Anything more specific or related to probability? You're right, of course, two coin tosses are independent. But I'm also looking for a sort of sense of probability here. Anyone else? What would you say are independent events? Okay, so two coin tosses are indeed what just happened. Hello, am I audible? Okay, my screen just sort of blanked out. Okay, yeah, sorry, I'm back. So, hello, am I audible? Okay, cool. Yeah, I just thought Zoom had sort of vanished. So two independent events would be also introducing a little element of probability in the sense something we'll talk about later. Say if I toss a coin the first time, then getting a heads in the first toss, and if I toss the same coin a second time, then getting tails in that toss. So these are two independent events, because we assume here that tossing the coin the first time and its outcomes are not related to tossing the coin the second time and its outcomes. This is an assumption because I mean, no one will ever really know. Maybe there is something in this great universe, some cosmological, there's some movement of stars that will make it change. We don't know that, but we do what we do best. So from the basis of logic, we assume that if you toss a coin the first time and the second time, the events when or the probability that you will say get a heads the first time and a tails the second time is not related. They're not related at all. Similar example would be if I throw a dice. If I roll a dice the first time, getting a 2 on the first roll and getting a 5 on the second roll, they are not related. They're independent. Yeah. Or for example, if I have a bag of a box of balls, say I had 5 yellow and 5 red. Yeah, a box with 5 yellow and 5 red. I can't see their colors till I take the ball out of the box. Let's assume that. So from those 5 yellow and 5 red balls, if I take out the first ball, or if I take out a ball once, then the probability that it will be yellow, the event that it will be yellow, and if I were to put that ball back and then take out another ball, so once I put the ball back, you have the same number again, 5 yellow and 5 red. So taking a ball out now and hoping that it is red, or calculating the probability that it will be red. These are two independent events again. The first scenario and the second scenario are the same because you have the same number of balls of the same color. So drawing first and then again redrawing with the same number are independent. What would not have been independent in this case? If I have 5 red and 5 yellow balls in a box, I take out a ball, and whatever that ball is, yellow or red, I keep it aside. I don't put it back in the box. Now when I draw or try to draw a ball, either yellow or red, from that box. Now there's a difference. Now the number is changed. Yeah. So now if I want to take out, or if I want to calculate the probability that the ball is red in the second draw, that is going to depend on the first draw. It's going to depend on whether my first draw was a red ball or a yellow ball. Now you don't have independent events. Is this clear? So if I do something that is going to affect an event later, then the first event and the second event are not independent. In fact, that is a general sense, that is a general challenge where, a challenge related to independent events. If there are two sequential events, then there may be a question mark on independent events. However, if there are sequential events, or if there are two events that are not at all related to each other in any way, then you will assume the events to be independent. Why do I say that? The question won't scream loud and clear, oh, this is an independent event. The question will obviously not tell you. You have to infer, you have to judge, and it'll be pretty clear in most questions that the event is independent. Yeah, is this okay? Let me know if you have any confusion with what I said, because what I said was not a mathematical concept. I'm just talking about logic right now. Is this clear? Okay. Okay, cool. Okay. Let's talk about events in general, and let's talk about set theory a little bit. The need to talk about set theory comes from the fact that, in fact, we'll discuss this in terms of PNC. What is happening? Say A is an event. A is the number of ways of doing some task or some event. B is the number of ways of doing another task or some event. So all the different ways in which A can be done and all the different ways in which B can be done are in these circles. I hope everyone has some basic idea about set theory, because when I represent these as circles, I am representing the set of the number of ways in which A and B can be done separately. And this area, the shaded area, are those ways that are common to A and B. Yeah, so the number of possibilities that are common to A and B are in the shaded region. Now, what happens when we talk about a mutually exclusive event? What is a mutually exclusive event? A mutually exclusive event is one in which there is no shaded area. The shaded area is also, in terms of understanding this is A and B. The region that is in A as well as B, the number of ways that are in A as well as B, and in terms of probability, it's exactly the same. If I were to say these were a set of probabilities, yeah, or if I were to calculate, yeah, let's not understand this set as probabilities. Let's say if these were number of ways, sorry, let me just, of getting A and B, then this shaded region would be, as I said, number of possibilities that are common to A and B. In a mutually exclusive setting, understanding two events that are mutually exclusive to each other, there won't be any A and B. So, on the roll of a dice, getting 2 and getting 4 on the same roll of dice, they would be mutually independent mutually exclusive to each other, and thus A and B would be 0. A and B, which is also known as mathematically A intersection B. This would be 0. And that is what we understand from mutually exclusive events. The probability that A and B are happening together is 0. And that is relevant because if you know the formula the basic formula of set theory, that A union B is A plus B minus A intersection B. Yeah. Then the probability that A union B is happening. And what does A union B represent? A union B represents that either A or B is happening. or or in terms of number of possibilities, that the possibilities of either of including either A or B, and this is not exclusive either A or B. The sense of A union B is always at least one of. At least one out of the two is happening. So it could be 1 out of 2 indeed, or it could be 2 out of 2. So A union B represents all possibilities in which at least one of A and B is happening. So this region that I have represented by dots here and here, this is the region where only A and only B are happening. So let me represent this as region 1. I'm representing this as region 1 because only one of the two possibilities is happening, and the shaded region as region 2 because exactly 2 out of 2, both possibilities are happening. Yeah. So A union B is always region 1 plus region 2 combined, all the area combined under the circle. You can see it like that. Is this clear? Is this clear, guys? So why I'm stressing this here is when you see a question in which the question says in how many or what is the probability that at least one of these happens. So it is possible that in that question you can apply, and there's a possibility that this formula would work and work well. So probability of A union B, the probability of event A or event B happening is essentially nothing but probability of A happening plus probability of B happening. So let me write this here. Apologies. Let me just. This is a generic formula and a very important one at that. So probability of A union B is probability of A happening plus probability of B happening minus probability of A and B happening, A intersection B. You subtract this because in P and PB you've already calculated P A intersection B once each. You've calculated once here. So you have calculated twice when you only need to calculate it once, so you subtract it once. So I am assuming that you understand this a bit because I am not getting into details with this. If you don't understand it, let me know. If you have no memory of set theory, it would be good if you let me know. But this is what the basic formula is, and the basic formula changes with regard to mutually exclusive events and independent events. And how does it change with regard to mutually exclusive and independent events? In mutually exclusive events, your probability of A intersection B vanishes. It's 0. Since the two events can't happen together at all, their combined probability has to be 0. The probability that both are happening has to be 0, and thus PA union B is PA plus PB. Very simply an addition. So what would be a good example? Let me just manage this first of all. Yeah. So a good example of this would be what is the probability of getting either a 2, well, I'm using the same example actually, of getting either a 2 or a 5 on the roll of a dice. Yeah, you roll a dice. What is the probability of getting either a 2 or a 5? Very, very basic example. Since on the roll of a dice you can't get 2 and 5, mutually exclusive events, thus probability of getting a 2 or a 5 is probability of getting a 2 plus probability of getting a 5. Very basic example. Probability of getting a 2 is using the basic formula, basic definition of probability, favorable events upon total outcomes, favorable outcomes upon total outcomes. So probability of getting a 2 is, favorable outcome would be getting a 2, which is actually just one favorable event. Total event would be getting anything from 1 to 6. So 6 total outcomes. Similarly, what is the probability of getting a 5 when you roll a dice? One favorable event, just getting 5 on the top surface, and total events 1 to 6, 6. So 1 by 6 plus 1 by 6, 1 by 3. Very simple. Yeah. let me just also talk about independent events, and then we'll discuss, and I'll ask you again if you have a problem. Okay, independent. In INDP means independent. I'm sure you guys smart people understand. So independent, what's different about independent events? What is different about independent events is that PA intersection B now becomes, so if you've attended my PNC class, um, PA intersection B is PA and B, two events happening together. Yeah. And if you remember, we talked about and fundamental principle of counting, and we always multiply it. When both events, when both the possibilities of both had to be multiplied and considered, and we do the same here. PA intersection B is nothing but PA into PB for two independent events. And of course, PA and PB are independent of each other. And of course, the formula now changes. The main formula, probability of A union B, probability of at least one of the two events happening, A or B, would be nothing but probability of A happening plus probability of B happening minus PA intersection B, which happens to be minus PA into PB. Yeah, and to give you an example, what is the probability? Let me get rid of this. What is the probability of getting a 2 on a roll of dice 1? The R1 means roll of dice the first time, and getting 5 on second roll. So what is the probability of getting 2 on the first dice and 5 on the second dice? Since this is AND, we multiply. So there are two different events. Probability of 2 on roll 1, written as P21, and P52 means 5 on roll of dice 2. You would probably do this intuitively 90% of the times. You just multiply this probability and this probability 1 by 36. I mean 1 by 6 into 1 by 6. This is 1 by 6 into 1 by 6, 1 by 36. Obviously, you could also have seen this as, since 2 and 5 are only one case out of 36 possibilities, I could have used PNC here. How my total outcomes are 6 into 6. Yeah. If I'm rolling a dice twice, in dice 1 there are 6 options. In dice 2 or roll 2, there are 6 options. So 6 into 6, I'm going to have 36 different combinations of numbers. And my favorable case, the only favorable case is 2, 5, and thus 1. So 1 by 36 is my answer. You could have also done it like this, or understood that these are independent events and multiplied their probability. Let me know if this is clear, or if you have any doubts.
Yeah, this is clear, but like if I want to use that formula, like how do you interpret it with the formula of P of A union B?
How do you interpret it with the formula?
Like these are two independent events, right? So
yeah. So in two independent events, PA intersection B, probability that A and B are happening, both are happening, is PA into PB. Probability that A is happening into probability that B is happening.
okay.
Yeah. So the only difference here is, see, the main formula is a formula empirically derived from set theory. We are not going to mess with that. Yeah, the one written here, the one that I'm just sticking. That probability A union B is PA plus PB minus PA intersection B. Hello?
Yeah.
So is this clear?
Yeah.
Yeah, so
Okay.
the only thing changes that generally changes in mutually exclusive independent events or other or events that you wouldn't classify as either mutually exclusive or independent would be this PA intersection B. This is what generally changes. And we'll see when we do questions, I'll tell you what I mean, in terms of the different kind of situations that we may have. Okay, good. Okay. Any other problem, guys? Are we P2 or 5? You written P2 or 5. Could you
No,
elucidate
I
what?
guess I was wondering that we will apply the A union B formula in case the question says what is the probability of getting 2 or 5, right?
Yeah.
What is the probability of getting a 2 or a 5 on the roll of dice the first time? Is absolutely union.
Okay.
Absolutely, yeah.
But that will be getting 2 or 5 on the first roll itself. Then there is no second roll.
I am assuming right now, considering the example we have taken, I'm assuming roll one, just one roll of dice. So how would this read if there were two rolls of dice? So what is the probability of getting a 2 or a 5 when a dice is rolled two times?
Yes.
Yeah, if this was the case,
I think we will just do here A will be 2 or 5 on the first roll, and B would be, I think, yeah, okay.
no.
I think we'll, yeah. So what we'll do is A will be getting 2 on the first roll, 5 on the second roll, and B would be getting
No, there are
5 on the
many more
first roll, 2
cases.
on the second roll.
So no. So if we are making cases, then we would have. So I'm trying to use the formula. When you ask this question, I was trying to think of the formula. Otherwise, there are many cases. If you have to make cases, then you have to make cases like getting. So yeah, let me write that. Let me write that here. I think we don't need the diagram now. Yeah, so the cases would be getting 2 on dice 1, getting 5 on dice 2, getting 2 on dice 1, not getting 5 on dice 2, getting 5 on dice 1, getting 2 on dice 2, getting 5 on dice 1, not getting 2 on dice 2. So I think that is it. Oh no, there are more. Getting 2 on dice 1, getting 2 on dice 2. So yeah. I mean, not getting 5 would be included.
Many
So,
cases,
yeah.
yes.
4 cases actually. No, 4 cases, because not getting 5. Oops, sorry. Not getting 5 on dice 2 already includes 2. So these would be 4 cases.
No, so like not getting 2 on dice 1, but getting 5 on dice 2. Is that also a case?
Not getting,
2
huh?
on dice 1,
Not getting 2 on dice 1.
but getting 5 on dice 2.
Yeah, have I not included dice 1 cases? I'm sorry.
I think there'd be too many cases, right? I mean,
There
it'll
would
get
be
too
too many. I'm
complicated.
sorry, I just haven't included the dice 1 cases. Yes, you're absolutely right.
It'll become too complicated.
5 2 dash. Oops. Yeah, there would be. Not getting 2 on dice 1, getting 5.
Not getting 5 on dice 1, getting
Yeah.
2.
I was still trying to think of more. I hope you're not repeating ourselves. No, we're not. Yeah, these are 2 more. 6, that's it. That should be it. Yeah. But there would be many cases. And is there a way to use this formula here? Probability of getting a 2 or a 5 in 2 rolls of dice. So the challenge here is, what is the event here? Is the first event roll of dice and another roll of dice? It isn't. Is the event getting a 2 in either of the dices? That just wouldn't work actually. This is actually a question. Yeah. This wouldn't work. This formula wouldn't work here
Yeah, it will work.
because these are two. I mean, it's hard to define an event here. Using P, A, union B, A and B need to be well defined here. And none of the events, I mean, whichever way you define that event, none of that event would help you get your overall answer here.
Right.
So I don't think there's another way other than doing cases. That's the first thing that came to my mind, but I thought maybe there's a way, maybe you can use the formula, but you can't use the formula here. There's no doubt. Okay, then let's go back. There always is ambiguity in PNC and probability. So don't worry, guys. I hope the last question hasn't scared you, but there is a sense of ambiguity, and there are, of course, there are limits to what we can calculate using the concept that we study, especially at GMAT. So. Okay, cool. So all that we have discussed has been summarized in this slide and the previous slide. So for mutually exclusive events, PA or B is PA plus AB. And for independent events, of course, it's PA plus PB minus PA into PB. I just want you to now try a few questions. So maybe I should repeat, especially considering that we discussed this in our PNC class. As a process, so sorry, let me just quickly talk about this here. As a process, there will be some questions in which you can directly use formulae. Yeah, the simplest ones. There will be others in which you need to make cases. Just simple formula, one step, two step won't work. You may need to make cases. And whatever I'm discussing is something we talked about in PNC as well. Yeah, so direct formulation or questions that are based on direct formulation, cases, case making questions. Then of course the one minus the unfavorable probability questions, which in PNC would be analogous to total minus unfavorable cases. As a process, this is what you generally need to do, either of these. And yeah, some of these questions would need these three or one of these three. So please try these three questions and then the next two questions that I'm going to throw at you. Let's quickly try 5 questions and then discuss and then talk about another concept. Any answers, guys? Have you attempted all 3 questions? Should I move the slide over to the next slide? Mm-hmm. Par, we should check the answer to your second question. And Abhay, you should check the answer to your third question. And of course, your answer to third question is not complete. But Par, you should definitely check your answer to answer the second question. Okay, for those who have not finished this yet, please take a snapshot. I am going to move the mouse over to the next. Dear student 674, please check the answer to both 2 and 3. And Par, we're going to discuss the answer, of course. But yeah, your answer to question number 2 is not correct. Let me just say that. You can check if you want. Take a screenshot first of all. I'm going to move my mouse over to the next question, next slide. So please take a screenshot now in the next 5, 4, 3, 2, 1 seconds, please. Thank you very much. Next slide.
From 6 yellow and 4. So in question 4, hello, sir, are you there?
Okay, time's up. Time's up. Time's up. Shall we discuss our 5 questions and their answers? Any answers to question 4 and 5? Okay, 5th is not correct. I'm afraid, sorry. The answer to question number 5 is not correct. And I just remember that I do have, I think, the answer key at the end. Yeah, here are the answers. So 5 is 1 by 7 to the power 6. 4, part 1 is 5 by 6. Absolutely correct. Part 2, we will discuss. I wonder if 4C2 into 61 is 1 by 10. Is it? 9 to 8. Is this your answer up here? 4C2 into 61, does this turn out to be 1 by 10? 4C2 is 6. 6 into 6. 36. This is 36 upon 942. No, it's not. It's not 1 by 10. Probably is 1 by 20. 2 is 1 by 20. And of course, yeah, this is nothing. This is the answer key. The answer of third question is 55 by 100 or 11 by 20. 2 is 5 by 12. And of course, 1 is 1 by 12. Let's discuss and see which question you guys had a problem in. Any problem in question number 1? What problem did you have in question 1? Is everyone getting 1 by 12? I think everyone is getting 1 by 12 here. Which question did you have a problem in, guys? Any problems with 2? It says from 1 to 100. Abhay. If it's between, when a question says, I mean, to be very honest, at GMAT especially, the question is not going to play with this between and from, and you wondering and guessing whether the ends are inclusive or exclusive. But in general, from 1 to 100 means including both 1 and 100. Between 1 and 100 means exclusive of both 1 and 100. Although, having said that, I would be very surprised if GMAT plays with that. Super, super surprised. Won't happen. So yeah, you do have 100 numbers here. So, any problems with this question? The others. Third question. Okay. I will discuss. Let me just quickly discuss all of them, I guess. Probability of choosing either a multiple of 2 or a multiple of 11 when one number is chosen at random from 1 to 100. So you want to choose either a multiple of 2 or a multiple of 11. Or both, actually. That is what the question means. So you could have you could have any number that is a multiple of 2, and there are 50 such numbers from 1 to 100, or a multiple of 11, and there are 9 such numbers. But then you're counting in both, in 50 and 9, you're counting numbers that are multiple 2 as well as 11. So question number 3 is a typical union question, PA union B question, where let me say that A is the event of getting a multiple of 2 and B is the event of getting a multiple of 11 when one number is chosen at random. So PA union B is PA, which means getting a multiple of 2, plus PB, which means getting a multiple of 11 minus PA intersection B, which means getting a number that is a multiple of 2 as well as a multiple of 11, which means A intersection B is getting a multiple of 22. So PA will be probability of getting a multiple of 2. There are 50 numbers that are multiples of 2. So 50 upon 100, 50 C1 upon 100, if if that seems more, if that seems more sort of empirical to you. 50 C1 upon 100 C1 is PA. 9 C1 upon 100 C1 is PB. And PA intersection B is getting a multiple of 22. There are 4 multiples of 22 from 1 to 100. So you subtract that. So minus 4 C1 upon 100 C1. So this is, of course, 50 by 100 plus 9 by 100 minus 4. 50 plus 9 minus 4 by 100. 59 minus 4 is 55 by 100. 55 by 100, you can simplify. You can sort of cut out the factor of 5, and therefore you get 11 by 20. Is this clear, Ayush and the others? I think, dear student 674, you also got an incorrect answer. Okay, excellent. Question number 2. What is the probability of getting a sum of more than 7? Okay, good. What is the probability of getting a sum of more than 7 when the same dice is thrown twice? Getting a sum of more than 7 actually means getting a sum of 8, or getting a sum of 9, or getting a sum of 10, or getting a sum of 11, or getting a sum of 12. More than 7 means that. Unfortunately, there's no other way in this question but to calculate. You need to sort of bend your back a bit here, but not that much, because getting a sum of 8 when you're throwing one dice twice, you can think of the possibilities. They would be 2, 6. Yeah, on the first roll you get 2 and then you get a 6. This is a different case from 6, 2. Getting a 6 and a 2 is very different from getting a 2 and a 6 here. Whenever there is an inherent arrangement here, in any question, and there is an inherent order, and the order here is throwing dice the first time and the second time. There is a first and a second. There is an inherent order there here, without a shadow of doubt. So 2, 6 and 6, 2 are 2 different cases. Similarly, 3, 5 and 5, 3 would be 2 different cases. So let me just write into 2. And then, of course, 4, 4. Yeah, so 2 cases, 2 cases, 4, 5 cases for 5 cases in which sum of 8 can be obtained. And similarly, getting a sum of 9 is 3, 6, 6, 3, so 2 cases, and 4, 5, 5, 4, another 2 cases. So 4 ways in total. Similarly, you can calculate for 10, 11, and 12. And in fact, they happen to be 3, 2, and 1, respectively. So the total number of ways of getting a sum more than 4 would be 5 plus 4 plus 3 plus 2 plus 1, which would be 15 by 36. And of course, you can simplify that. 5 by 12 is the right answer. Yes? Is this clear? I think I saw a couple of incorrect answers here. Okay, good. The next slide. Any problems here? 3 balls are chosen from 6 yellow and 4 red balls. What is the probability that at least 1 ball is red? And exactly 2 balls are red. Any problems here with this question, guys? These questions? Okay, at least 1 ball is red. Can I say, like we discussed, getting the probability of at least 1 ball is red can be seen as 1 minus probability that no ball is red. And that, of course, can be seen as 1 minus probability that all are yellow, all balls yellow. Because if you calculate the probability that all are yellow from 1, you get the probability that at least 1 is red. So, and therefore this comes out to be, question for part 1 is nothing but 1 minus probability that all are yellow. So 6 yellow, you had 6 yellow, and you're choosing 3 balls from those 6 yellow. So this would mean probability of getting all yellow would mean favorable cases would be from 6 balls, you choose 3 balls. While total cases will be from the 10 total balls, any combination of 3 balls may be chosen. Is this clear? Is this clear, guys? 1 minus 63 upon 10c3. If you solve this, I think you're going to get 5 by 6. So, yeah.
I just want, I want to make this clear. If it is given that 3 balls are chosen, we are taking all 3 at once, right? We are not taking one, keeping it back, then taking second, keeping it
Not
back.
at all. That case will be specified. The question has to specify that.
Okay.
Yeah. In fact, I'm expecting one more question when I'm given this. I was expecting 2 questions. One was yours. I'm happy that you thought of this question. I'm sure many people did not think at all, or many people did not need to think because it's not given. Any other question with regard to this question? Did anyone else think of any other question when you read this question? The other thing that I want to mention with regard to this question and such questions is that if the question doesn't say that if the question only says 6 yellow and 4 red balls, you are going to assume there are 6 distinct yellow and 4 distinct red. You will not think of same balls in that sense, You will not think that these were similar in nature or they are the same balls for one reason or the other. In fact, here we're not talking about arrangement at all, or here we're not even talking about. The probability won't be affected in general, but whenever the question is written like it has been written here, you assume that the objects shared in the question, given in the question, they are distinct. Distinction is default, similarity is not. If objects are similar, the question will tell you. If the question is not saying anything, you assume they are distinct. Okay, that's something to keep in mind, guys. Any problems with question 4 part 2? You want the probability that exactly 2 balls are red. So essentially what you want is you want the probability that 2 are red and 1 is yellow. Exactly 2 red means 2 red, 1 yellow. Yeah. So from the draw of 3 balls, getting 2 red would mean from 6 yellow getting 2, so 62 ways. And from 4 red, oh, sorry, this is not 6, this is 4. This is 4. So yeah, from 4 red getting 2 red, so 4c2 into 1 yellow would mean from 6 getting 1, so 61 upon 10c3. 10c3 remains the total number of ways. Yeah, this is what, this is how the answer has been expressed as well. So if you want to calculate, go ahead and calculate the, sort of number. So yeah, that's it. Question number 5. From 7 people in a group, what is the probability that they were all born on the same day of the week?
Sorry, this is also correct, right?
What? 4 by 10 to 3 by 9 to 6 by 8?
Yes. Or do we need to change anything in this?
Yes, you do. What you've taken here is 4 is 4 by 10 means that you've drawn. So what you've taken here is the order actually.
Mm-hmm.
The problem with this is that I don't think this is going to give you the right answer. Of course, other than that, there is no real sequence away. I think you missed my discussion with Parv and with the others when I said that when the question says that 3 balls are chosen at random, I think maybe it could have added at random. But if it hasn't, it doesn't need to. When 3 balls are chosen is written, it means that it's not sequential. There's no sense of sequential. It's not as if they are being drawn one after the other.
Okay.
Because then you would need the question to clarify whether they are being drawn one after the other, with replacement, without replacement, and so on and so forth. So your answer seems to suggest that balls are being drawn without replacement, but that is not a sense I get from the question. It's not mentioned anywhere. It has to be mentioned. And if it's not mentioned, then 3 balls are just drawn at random. So imagine, you sort of blindfold yourself and you put your hands in a box that has 6 yellow and 4 red balls and draw out 3 balls. That is what this question seems to insinuate. That is what it suggests. There's no sense of sequence. So your answer is not correct. And the method is not correct either. This is most definitely an NCR question. So from from 4 red, you need to draw 2. And from 6 yellow, you need to draw 1. That is the favorable case. And of course, total case continues to be 10C3. Yeah, I hope I've answered your question.
Yes.
Okay.
I'm just trying to understand this logically, basically.
What are you trying to understand logically?
No, I mean, in the end, we are drawing 3 balls, right?
Yes.
So if the first one that we draw is a red one, then the probability of getting a red is 4 by 10.
Yes. The probability of getting a red the first time is an independent event. So it will be 4 by 10 without a shadow of doubt.
And if we draw it a second time, it will be 3 by 9.
Absolutely correct.
And the third one then has to be a yellow.
This is where the problem comes in. What if the first ball you draw is a red ball? Is a yellow ball. Yeah.
Yeah, so in that case, it
You will
becomes
have a different answer. Yeah.
I think the answer will remain the same in all the 3 cases, right? And irrespective of which ball you draw.
This is the anomaly of, I don't want to get into this. This is the anomaly of choosing at random and choosing sequentially. But that still wouldn't work here because you have 2 different objects. But in general, if the question only said, so anyone who understands this is a bonus. This is like the water cooler conversation you have, water cooler gossip. But the only thing, this is water cooler gossip about probability, and the water cooler gossip about probability is that so if the question read 3 balls are chosen at random from 6 yellow balls, say, if that is all the question was, and you had to calculate the total number of ways in which that could be done. Okay. So from three yellow balls need to be drawn from 10 total balls. Let's say that is the question. Then 6C3 upon 10C3, let me just forget about the red balls and the other details. Yes. 6C3 upon 10C3 would give me the same answer, which 6C3 upon 10C3 is, there's no sequence here, just choosing 3 balls at random. But if you calculate the answer sequentially, you would have got the same answer.
Right.
But the problem with that is you change a few details and you will not get the same answer, because essentially in terms of process, that is incorrect. So that is where my sort of objection, or my advice was when I saw your answer, that as a process it's not correct. And of course, messing with the process doesn't make sense, because the question is going to test that.
If we apply the combination formula, then the sequence becomes irrelevant.
Yep, absolutely.
And here the sequence is relevant.
The sequence is not relevant in this question.
No, I mean the process that I have applied, in that the sequence becomes relevant. That is why it match in the answer.
Yeah. If the question suggests that sequence is relevant, then you solve it like the way you did. Otherwise, you don't.
Okay.
Okay.
Cool. Okay.
Yeah. Question number 5. From 7 people in a group, what is the probability that they were born on the same day of the week? There are many ways of doing this question. The simplest and the most relevant, and the others are a little indirect. So the most direct way of calculating this probability is firstly seeing the total number of cases, total outcomes. Now, what will be the total outcomes? Now, the first person has sort of 7 options, or the 7 possibilities of the first person being born in terms of the number of days from Monday to Sunday. So the first person may be born on any day from Monday to Sunday, 7 possibilities. The second one also has 7 possibilities. The third one also has second. All 7 people have 7 possibilities. And we'll not add here. We are not talking about considering only the first person or the second or the third. We are talking about all 7. We are talking about the birthdays of all 7. And thus we'll multiply. My total outcomes is going to be 7 up to the power 7. Yeah. For the 7 possibilities of each of the 7 people multiplied, 7 to the power 7 is total possibilities. What is the favorable possibility or the favorable outcome? Let me write that as F4. Favorable outcome is all of them being born on Monday, or all of them being born on Tuesday, or all of them being born on Wednesday, and so on up till Sunday. Yeah, so the first is also born on Monday, second also. So these are actually just 7 favorable cases. These 7 favorable. So Monday for all 7, 1 favorable case. Tuesday, second favorable case. Wednesday, then up to Sunday, these are 7 favorable cases. My probability has to be 7 upon 7 to the power 7, 1 by 7 to the power 6. Yeah, is this clear? Is this clear, guys? You could also have seen this as, so, if 7 to the power 7 is clear, 7 to the power 7 is, of course, the total probability, the total possibilities. Favorable possibilities, favorable outcomes would be if we are considering the birthday of the first person. Now, for the favorable outcome, the first one has any, or has all 7 options. He or she could have been born on any day from Monday to Sunday. So 7 choices, 7 choices. But once a choice is fixed, once the first person, chooses from the 7 and say, we say that he or she is born on a Wednesday. Now, all the others don't have any choice. So now the number of ways in which, or the number of possibilities to get our favorable outcome for the second person is just 1. Has to be the same day as the first person. For the third person, it will be 1. For all others, it will be 1 each. So this is also one way of seeing this fundamental principle of counting again. So 7 into 1, 1, 1, 1, 1, and so on. Again, it's 7. 7 upon 7 to the power 7 remains the same answer. Let me know if you have any doubts, guys, here. Let me know if you have any doubts. Okay, all clear. Very good. Now let me ask you a seemingly simple question. If I toss a coin 3 times, yeah, what is the probability that I'll get 2 heads? 2H means probability that on 3 of those tosses you have 2 heads. Try this one right now. I toss a coin 3 times. What is the probability that I get 2 heads? No, it's not at least 2 heads per. It is exactly 2 heads. What is the probability of getting exactly 2 heads? Yeah. So student 674, I'm afraid 1 by 8 is not the right answer. 1 by 8 for sure is not the right answer. And Rupen, Abhay and Parv, would you like to sort of share how you got this answer? How do you get this answer? 3 by 8.
So if we toss thrice, yeah. So he has written the cases.
Total 8 cases, H, H, T, H, T, H, T, H, H. Excellent. And how total 8 cases, Abhay?
1 by 2 into 1 by 2 into 1 by 2.
1 by 2.
Basically 2 into 2 into 2. Basically.
Okay.
I was trying to apply the combination thing, but I couldn't roll my head around it, so I thought of taking the simpler way.
Okay, excellent. So this definitely works. In fact, you could quickly write down, like Abhay just did. You could quickly write this down and see that these are all the possibilities: tail, tails, tail, 3 tails, or 2 tails and 1 head, which would mean this, or 2 heads and 1 tail, which would mean this, or all 3 heads. These are all the 8 cases. Your 3 favorable cases must be these 3. And therefore, 3 by 8. Now, what if I were to change the values a bit? What if I were to say you toss a coin 15 times? What is the probability of getting 3 heads? Now, how will you calculate? If I toss a coin 15 times, what is the probability of getting 3 heads? How will you do this? Before you start doing it, please tell me how you would go about solving this question. Okay, no answers. Any guesses? I'll be more than happy to hear the guesses. One minus 13.
Basically, we will need to calculate further, obviously. What is the probability of each of these events?
And what are these events? Is this C2? What is T? Sorry?
No. So 13 tails and 2 heads, plus 14 tails and 1 head, plus 15 tails. So getting 15 tails.
No.
Divided by 2 power 15.
Sorry. I'm not asking for at least 3 heads. I'm asking for exactly 3 heads. What is the probability that you will get exactly 3 heads when you toss a coin 15 times? How would you go about this? Because of obviously checking all possibilities for 15 times is just madness. That is not possible in the environment that we're talking about.
Just taking a wild guess here. Is it something like 15C3 divided by 2 to the power 15?
15C3 divided by 2 to the power 15. Maybe.
Okay.
Why 2 to the power 15?
The number of cases is 2 into 2 into 2 up to 15 times. Now the only question is how do we select head?
Okay.
Only
Okay. Let me ask you the same question with a slight change. Let's say the probability of getting a head. Now we are not using a unbiased coin. We are using a biased coin. Let's say the probability of getting a head in this coin is 1 by 3, and the probability of getting tail is the remaining 2 by 3.
Okay.
Would your answer still be the same over here? So I've taken a new coin, biased or loaded coin, whatever you want to call it, in which the probability of getting a head is not 1/2 and tail 1/2, as is normally the case. Probability of getting a head is 1/3 and getting a tail is 2/3. And you toss this coin 15 times. What is the probability of getting 3 heads?
I think then your answer should change, right?
No, I don't know. That's something you would tell me.
No, I think it should change. Yes.
How? And this is your answer. It was correct, absolutely correct, and very good. Your answer shows the inherent problem with a coin question, because in that the probability of getting a head and the probability of getting a tail is equal, and thus you can actually ignore probabilities in that question if you just focus on what is happening, on the basic numbers. So 3 heads out of 15 would have given you the same answer as 3 tails out of 15. It would have been exactly the same, simply because the probability of getting a head and tail is equal. But that is what we need to challenge, So what if it is not? So let me talk about this very quickly, using the example that we had done here. Although this was very small and very basic values, but nevertheless. Another way of seeing this question is going back to my original values and going back to the original unbiased coin. If I toss a coin 3 times, the probability of getting 2 heads is, in fact, like Abhay had written here, getting 2 heads is essentially something like getting 2 heads and getting 1 tail. Now, let me just do one thing. Let me just calculate, so, sort of break the question into 2. Let me first see how many such arrangements are possible. Now, they happen to be 3 written here as well on your screen, but they happen to be 3 for a reason. They happen to be 3 because what you're trying to do, essentially, if you look at these 3, you are trying to arrange 2 similar H and 1 T in a straight line. This is very similar to the PNC concept that we had covered, in which you try to find out the number of words in which, some words are similar. So if you remember, for all those who had done that class, we had solved a couple of questions on mathematics, in which M was, there were 2 M's, there were 2 T's, there were 2 A's. So this is what I'm talking about. Getting 2 heads and 1 tails essentially means arranging 2 H and 1 T in a straight line, which is nothing but 3 factorial upon 2 factorial. So what I'm doing firstly is finding out the number of ways this would be possible, which would be 3 factorial by 2 factorial, which would be 3 actually. And then multiplying it by the probability of any one. Yeah. So my total probability can be seen as, if I were to look at it like this, just calculate the probability of any one event and then multiply it by the number of times it is happening. The same, because it's almost essentially the same event, the probability won't change. So the probability of getting a head in the first toss and the head in the second toss and the tail in the third toss will not be different from getting a head in the first toss and a tail in the second and a head again. The probability of each of these 3 events, the third being this, tail, head, and head, in the first, second, and third respectively, is always, so head, sorry. So head here, getting a head in the first toss is 1/2. Then again, getting a head in the second toss is 1/2, and then getting a tail in the first toss is also 1/2. So 1/2 whole cube. And the same holds for sequence 2 or sequence 3. So my answer will remain 1/2 whole cube, which is 1/8. So my overall answer is 3, which is the number of ways this event can be managed, into 1/8, which is the probability of any one of the event happening, 3/8, which is what we had, obviously. Yeah, let me use the same basic structure of the question and talk about calculating if a coin is tossed 5 times, what is the probability that you get 3 heads? Let's talk about this. Similar structure. So if a coin is tossed 3 times, probability of getting 3 heads would mean something like this: getting a heads, 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 and tails, or the various combinations of this: a head, tail, head, and so on and so forth. So what are we going to do as a rule, rather than remembering a formula, to be honest? Rather than remembering a formula, just understand that you're talking about arranging this, and the total arrangement of this would be 5 factorial upon 3 factorial for the 3 similar h's and 2 factorial for the 2 similar t's. And this also happens to be 5c3. This is what 5c3 is. But if you want to remember in terms of arrangements, you can. So the number of arrangements that are possible for this into the probability of any one of these events. So just calculate the probability of this event happening. This event matlab h, heads, and then tails. So in the first toss, getting a heads is 1 by 2, then again 1 by 2, 1 by 2, 1 by 2, 1 by 2, this is 1 by 2, whole to the power 5, 1 by 32. So my answer is going to be 5c3 into 1 by 32. And of course, you can simplify this further. Is this clear? And therefore, what I want to recommend you do in such question is, your total probability is always going to be the number of arrangements possible into your probability of any one of the arrangement. Probability of any one arrangement. That is what we've been doing, in the last 2 questions. Calculate the number of arrangements. Multiply that with the probability of any one arrangement, and you get your answer, 100%. Is this clear? Is this clear, guys?
So so you gave an example when the probability of head was 1 by 3 and for tail 2 by 3.
Yeah.
I think then this will also change, right?
No, it won't. It'll be exactly the same.
I mean, instead of 1 by 2 raised to the power 5 or whatever, so it would be as per the heads and as per the tails.
So let's take it here. Let's take that for this question. Say I want to calculate the probability. Get rid of this. Yeah. So let me calculate the probability of getting 3 heads in 5 tosses, when the probability of getting a heads is 1 by 3, and therefore tails is 2 by 3. So firstly, doing the same, from 5 possibilities, you want to get 3 heads, the answer will be exactly the same. Number of arrangements would be 5 factorial upon 3 factorial into 2 factorial. However, the probability would change, because now getting a heads in the first 3 tosses is going to be 1 by 3 into 1 by 3 into 1 by 3, 1 by 3 whole cube. And then getting a tails is going to be 2 by 3 into 2 by 3, 2 by 3 whole square. That is the only real difference. Yeah, is this clear?
Yeah, okay.
So in fact, in such questions, it is foolish to calculate your total number of outcomes, because you won't be able to calculate your total number of outcomes. These questions just don't work like that. So the total number of outcomes in this question are not 32, in the sense that your total arrangements are not 32. I mean, using fundamental principle of counting, it may seem like you have toss number 1, toss number 2, toss number 3, toss number 4, toss number 5. In toss number 1, how many options do you have? How many outcomes? 2 outcomes, either a head or a tail. In toss number 2, how many outcomes do you have? 2 outcomes. Getting a head or a tail, 2, 2, 2, 2, 2 each times, and therefore 32. No, this is incorrect. Simply because if the probability is 1 by 3 and 2 by 3, you will not get the right probability. I mean, these questions don't work like that, unfortunately. Is this clear? Do not use in such questions, I'm repeating, total outcomes, favorable outcomes, but total outcomes, you will not be able to get the answer. Okay, then let me just throw these two questions your way. Question number 6 and question number 7. Please try question 6 and 7. We've already done question 8. It's the same question. I mean, it's the same set of values that we had discussed. So you can ignore 8th, of course, but please do try 6 and 7. Shall we discuss? Let's discuss, guys. Any answers to question number 6? 2. What is the answer to 2 up here? Absolutely correct, guys. (15 into 14 into 13). or you're definitely missing something. What are you missing? Abhay, I just didn't get what you had written here. Sorry. (15C3). 15C3, not 15C2. Is absolutely
yes.
yeah. 15C3 is it's absolutely correct.
So this is what I wrote above in a more complicated fashion.
Okay, yeah, I get it now. Yeah, 15 to 14 to 13. See, I would recommend you stick to 15C2 format because I think I shared this last time. Where in questions where the calculations are lengthy or you're dealing with big numbers, you would, I mean, the GMAT would not expect you to calculate the answer. It will just give you options in terms of 15C2 and 15C3 and so on and so forth. Simply because it doesn't provide a calculator. So, okay, question 7, quick, 2 minutes. You have 2 minutes to solve question 7. Let's see what the others have to say. And the answers are here in front of you, your screen. 6 part 1 is here, 6 part 2 is not here, sorry. But question 7 is indeed 5 by 6. So do you want me to discuss question number 7, guys, or 6? Let me know right now.
6th, second part.
6th, second part. If the probability of hitting a target in practice is 1 by 3, then after 15 attempts, what is the probability that the target is hit exactly 3 times? That's part 2. Let's discuss part 2 and then briefly discuss part 1. Target is hit exactly 3 times. So let me just sort of denote hitting the target as H and missing the target as M. So hitting a target exactly 3 times means something of this sort. Hitting, and then missing 12 times. Or any other combinations, or it could possibly have been hitting, missing a few times, then hitting again, then hitting somewhere in the middle and missing, and something of this sort.
So if I go by this approach, like I get that, I get the answer. But like if I just if I start solving it this way, suppose the first for the first time I hit it, so the probability would be 1 by 3. So the probability of 3 hits would be 1 by 3 raised to the power 3, and for the another 12, it would be misses. So it would be 2 by 3 raised to 12.
Yep.
So then it should be 1 by 3 raised to 3 into 2 by 3 raised to 12.
That's for the event you've chosen. So please try to understand what this is a probability of. This is a probability of hitting in the first 3 shots and missing in the next 12. That is exactly what the probability is, what you just said.
Okay.
There are so many more events, that are favorable. Yeah.
I got that. Yeah.
So that is what essentially, we have been doing. So, this is one such favorable event. There may be another event in which the opposite. So the second favorable event could be miss, hit. A third event, favorable event could be hitting, missing, and then hitting again, then missing again, then hitting, and then, the remaining number of misses from total 15. There could be a fourth, there could be a fifth, there could be many. what I want to say essentially here is, in all such questions, without a shadow of doubt, whether you calculate the probability of event 1, event 2, event 3, these favorable events, what is their probability going to be? What is the probability of event 1? Hitting is 1 by 3 into 1 by 3 into 1 by 3, and then into 2 by 3 into 2 by 3, 12 times. So 1 by 3 to the power 3 into 2 by 3 to the power 12. This was the probability of event 1. What is the probability of event 2? Which was miss 12 times and then hit it. It's 2 by 3 to the power 12 into 1 by 3 whole cube, exactly the same. What is the probability of event 3? Hitting, which is 1 by 3, then into 2 by 3 into 2 by 3 and 2 by 3 again, then into 1 by 3 again, then into 2 by 3 for the miss, then this is a hit, so into 1 by 3 again and so on. Essentially, all of them are going to be 1 by 3 whole cube into 2 by 3 to the power 12. This is the probability of one favorable event. Multiply that by the number of favorable events and you get your answer. And the number of favorable events is going to be 15. I either understand this is going to be 15C3, or if I understood that this is arrangements of 3 similar H's and 12 similar M's along a straight line, I can also say that this number that I'm going to multiply is nothing but 15 factorial. 15 objects have to be sort of arranged in a straight line, out of which 3 H are similar, so 3 factorial for that, and 12 M's are similar, so 12 factorial for that. Is this clear? Yeah, Parv, especially since...
Yes. Yeah.
Excellent. Okay, any problems with question number 7? Any problem with question 7, guys? Okay, cool. That's it from my side in that case. There isn't much else, and we may see some other miscellaneous probability later. But really, for GMAT, this is more than enough. This is more than enough. You'll see many formulae. If you refer to books, I would recommend you ignore all of them. You will see formulae for this as well, and you don't need them, because if the question gives you, different twists or different terms, then you may not be able to apply the formula. And you can also ignore other formulae for Bayes' theorem or conditional probability. You don't really need them. Yeah, so I will share a sheet that has a few different problem types that we can discuss if you have doubts with that, then. But yeah, that's it. I'm not going to sort of cover anything else in probability. Is this good, guys? Is this okay? Is this clear? Let me know if you have any doubts.